This week we will be learning about t-tests. We'll do some work in SPSS, our new software system, and run some one-sample t-tests. So a t-distribution is very similar to what you're used to with the normal distribution or the z-distribution. There's two differences that are key though between the t-distribution and the z-distribution. First is that when a sample size is small, say you have less than 25 people in your sample, t-distributions are more flat in the middle, so the top of the curve is going to go down, and they have higher ends, so the tails will actually come farther off of the X line, okay? So essentially they're going to look more platykurtic than a normal distribution. And then secondly, when the sample size is large, i.e. over 120, the t-distribution is virtually identical to the normal distribution. So if we have, say, 480 people in our sample size, we could either use the t-distribution or the z-distribution. However, if our sample size is less than 120, we have to use our t-distribution in order to get our correct values. Our t-distribution is found in Appendix B. Just like we had Appendix A and we were able to find our probabilities of our z-scores, Appendix B allows us to find our probabilities of our t-scores. And we'll go into how to read that appendix in a minute. So we use z-scores to determine the probability of randomly selecting a sample with a particular mean on a variable from a population with a given mean on the same variable. Or, said in other words, we use the t-distribution to determine the probability of randomly selecting a sample of a given size, say 30, with a mean IQ score of 12 from a population if we know the population standard deviation. Similarly, we use the t-distribution to generate t-values to find the same type of probabilities. Okay, so the probability of selecting a sample of 25 students with an IQ score of 12. However, with a t-distribution, we do not know the population standard deviation. All we have is the sample standard deviation, so we have to estimate the population standard deviation from our sample. Why t-distributions are helpful is because we're rarely going to know population parameters such as standard deviation. So essentially, you can estimate the probability of getting a sample with a mean of X, even if you only have samples and information from your even if you only have data from your sample. Okay? So, essentially, this one summarizes which one do you need to use. If the first question you need to ask is, do you know your population standard deviation? If the answer is yes, you're going to use the z-distribution in Appendix A and your z formula. If the answer is no, you're going to use the t-distribution in Appendix B and your t formula. Notice that the only difference between your z and your t formula is the denominator. We have the population standard error of the mean on the bottom of z in purple, and we have the standard error of the mean of the sample on the denominator for the t-value in yellow. Okay? So what is a t-test? Essentially, it's a statistical test used to compare two means to see if they are statistically different from each other. Technically, the definition is any statistical test that uses the t-family of distributions. There are other tests that will use this, like correlation coefficients, regressions, and other types of t-tests. We're only going to cover a few in this class. But essentially, what you want to know is that it's a statistical test used to compare two means to see if they are significantly different from each other, the commonly used definition. So a one-sample t-test. The purpose is to compare one sample mean to a known population mean. So essentially, for a one sample t-test, we need to know our population's mean, say how many miles on average GM's new fleet of cars gets, miles per gallon, and we want to compare our sample mean, So I took 10 cars and I drove them 100 miles, and now I have a miles per gallon. So does that sample mean, is it different than the population mean that GM put out? We have two different variables. We have our independent variable. This is going to be our grouping variable. What this means is for each category, do I know if it's a sample or a population? And then our dependent variable is our continuous variable. So for that example, it's going to be miles per gallon. Okay, so here's another example. You know the mean income of all Tennessee residents is $38,000. We want to know, do Tennessee high school teachers have a statistically different income? This is rarely used in research, and normally it's not used because we typically don't know the mean of all Tennessee residents' incomes, okay? We typically do not know our population parameters. So we'll go into this one sample t-test because sometimes we do, and it also is a building block for the t-test we'll get into a little bit later. All right, so a one sample z-test, that's what we've been doing this for the last 2 weeks, and a one sample t-test. So a one sample z-test is when you know the population standard deviation, okay? So an example might be, if you want to know how our stats class did on a national math achievement test with a mean of 75 and a standard deviation of 10 when our class average was 78. So we can see from this example that we do have our population mean, which is 75, and we also have our population standard deviation, which is 10. On the other hand, we might have a one sample t-test when you don't know your population standard deviation. So an example would be, if you want to know the class average and standard deviation of our stats class on a national math achievement test was 80 and 7 respectively. So we know that our class's average mean was 70 and our class's standard deviation was 7. And you want to know how our class did relative to the national norm with a mean of 75. Okay, so in this one we can see that we do not have our population standard deviation, so we would need to run a one sample t-test. When we're running statistical tests, there are a number of assumptions that each test has. A one sample t-test has 3 assumptions. The first is that the dependent variable, or income level for our Tennessee resident example, is continuous. Okay, so it's either on a ratio or interval scale. Next, we have the assumption of independence. Our observations are independent of each other. This assumption is relatively hard to test. However, if we know that our data was collected at random without replacement, we can assume that we meet our assumption of independence. And thirdly, we have normality. We want to assume that our dependent variable, i.e. income, is normally distributed. If our sample is large enough, we automatically assume we meet this assumption for a one sample t-test. Degrees of freedom. We're going to get into this in a minute, but I want to teach you the definition first. So degrees of freedom is an estimate of the number of independent pieces of information that went into calculating the estimate. Okay? So for a one sample t-test, this is the part you need to know. The degrees of freedom is n minus 1. So our sample size minus 1. Okay, so if we have a sample size of 25, our degrees of freedom for a one sample t-test will be 24. Okay, so let's look at Appendix B. Appendix B, which is in your e-courseware as well as in the appendix of the book, looks a little different than our Appendix A with our Z distribution. We have 2 different things going on. We have our alpha levels for our two-tailed tests on this line, and then we have our alpha levels for our one-tailed test on this line. On the side, we have our degrees of freedom. Okay, so let's say we were interested in finding if teachers' incomes significantly differ from that of the average Tennessee resident. We had a sample of 25. So our degrees of freedom is n minus 1, so 25 minus 1. Okay. And it's a two-tailed test because we're interested in seeing if they differ, not if they're greater or less than. And we have an alpha of 0.05. Okay, so we're going to go to our two-tailed test line here, find our alpha of 0.05, and go straight down until we find 24 degrees of freedom. And we can see that that T critical value is 2.064. Okay? So that's how we would use our Appendix B. Let's do another one. Say we had a one-tailed test with alpha of 0.05 and a sample size of 12. So if we had a sample size of 12, our degrees of freedom is going to be 12 minus 1, so 11. We'll go to our one-tailed test at an alpha of 0.05 and go down the line until we can see that our T critical value is 1.796. Okay, so now we'll do some examples and how to solve one sample t-tests. Very similar to how we did z-scores and z-testing. Okay, so example 1. Suppose you know the average American man exercises for 60 minutes per week. You collect data from a random sample of 25 men at a local gym and found that they had a mean of 65 minutes of exercise per week with a standard deviation of 10. You want to know if the amount of time the men at your gym exercising is different from the American population. Set an alpha at 0.05 and use the 5-step hypothesis test to answer the question. Okay, so a couple of things we need to think about first. What is our sample size? We can see that it's 25 men. So what would our degrees of freedom be? Degrees of freedom for a one sample t-test is n minus 1. So that's going to be 25 minus 1, so 24. And do we know the population standard deviation or the sample standard deviation? Well, we can see that the average man exercises 60 minutes per week, but we do not have the population standard deviation. So this means that we will need to run a t-test in order to find out if these two groups of people are going to differ significantly. So we're going to start with our null hypothesis. There are two different ways that you could write this. If you remember from the previous slide, the average American man exercises for 60 minutes. So our first null hypothesis that we could write, these are just two examples, either one is fine, is that the mean of our population that our sample represents equals 60, or that the mean of our group equals the mean of the population. Okay? And we would also write that in words. The average amount of time the men at my local gym exercise is the same as that of the men in the American population. Alternative hypothesis, very similar, just cross out your equal sign. The mean of the population that my men in my sample represent is not equal to the mean of American men, or that my sample mean is not equal to 60, which is the amount that the men in the American society exercise. So the men at my local gym exercise a different amount per week than the average American man. We want to set the criterion for rejection. Again, it's alpha is 0.05, just like we saw before. And then we're going to use our Appendix B to find our T critical value. What is our region of rejection for this example? So we have 25 men, right? And our degrees of freedom is 24. It's a one sample t-test. So we'll use the alpha for a two-tailed test at 0.05 and go all the way down here to 24. And we will see that our T critical value is going to be 2.064. So we can see that our alpha is 0.05 and our T critical value is 2.064, which is going to be where we set the region of rejections. So we can see if we draw our graph, our T critical value is going to be negative 2.064 on the left and positive 2.064 on the right. So now we need to compute and report the test statistics. So the first thing we're going to do is calculate our standard error of the mean for our sample. So we need our S, which is our standard deviation of our sample, and our sample size, which is 25. So 10 divided by the square root of 25 is 10 divided by 5. So our standard error of the mean for our sample is 2. And then we need to calculate our t-value. So we have our sample mean minus our population mean divided by the standard error of the mean of our sample, which is 65 minus 60 divided by 2, which is 5 divided by 2, which is t is 2.5. So we can see that our t observed value of 2.5 falls within the region of rejection, so we know that we're going to reject the null hypothesis. So we reject the null hypothesis because t, and then we write the degrees of freedom, 24, equals 2.5, which falls within our region of rejection. So now we're going to report our conclusion. And this is how we report it. A one-sample t-test was conducted to determine whether or not the amount of time 25 men at a local gym exercise differed significantly from the amount of time the average American man exercises. An analysis produced a significant t-value. T subscript 24, which is our degrees of freedom, equals 2.5, comma, p is less than 0.05 because we set our alpha at 0.05. An examination of the means reveals that the men at the gym exercised, mean equals 65, standard deviation equals 10, more than the average American man, m equals 60. So that is how we conduct a one-sample t-test. Let's do another one together. The University of Memphis president randomly sampled 17 seniors to take a nationally normed college exit exam called Out of Here, which had a mean of 100. The president has given you the following data to determine if U of M grads are scoring equivalent to the national standards. Set alpha at 0.05 and use a 5-step hypothesis test to draw a conclusion for the president. Also identify the independent and dependent variables and whether it's a one- or two-tailed test and the degrees of freedom. So here's our data set. We have 17 different students, and here are each of their out of here scores. So what formula are we going to need? Obviously, we need our t formula because we do not have the population standard deviation. So do we have all the values we need for that formula? Do we have our mean? No. Do we have our population mean? Yes. Do we have our standard error of the mean? No. So what other formulas are we going to need? We're going to need to find our mean first and our standard deviation, our standard error of the mean. Okay, so first we're going to calculate the mean. We're going to sum all of the scores, which is equivalent to 1,870, and divide it by our sample size of n. So we get a sample mean of 110. Then we need to calculate our our sample standard deviation. Again, we did this the first half of this course. So we would take the sum of all of these individual scores minus the mean squared divided by n minus 1, which is going to be 2,206, divided by n minus 1, 17 minus 1, and take the square root of that. So the square root of 137.875 equals 11.74201,857. So now we're going to calculate the standard error of the mean, which is s divided by the square root of n. So we take this value, the standard deviation of our sample, 11.7420, divided by the square root of 17, which is dividing by 4.1231. So our standard error of the mean is going to be 2.84785781, or we'll round it to 2.8479. Okay, so we have to do all of that before we can begin our t-test. So now let's go over here and we're going to state our null hypothesis. First, we're going to use symbols. So the population of the University of Memphis is equal to 100, right? Because 100 is our population mean. Or the population mean for the American people is the same as the population that our sample of University of Memphis students represents. In words, the seniors of the University of Memphis will do the same on the out of here test as students nationwide. Alternatively, same symbols, just put the not equal sign, and in words, the seniors from U of M will score differently than students nationwide on the out of here test. Okay, so now we need to state the criterion for rejection. Is it a one-tailed or a two-tailed test? What we want to notice is we're just asking if they're going to score differently, not better or less than. So our test that we're going to be running is a two-tailed test. So we need to state the criterion for rejection. So the first thing we're going to do is set our alpha of 0.05. That's what our problem told us. And now we need to go find our t critical value. So our sample size is 17. And it's a two-tailed test with an alpha of 0.05. So our degrees of freedom is going to be n minus 1, or 17 minus 1 is 16. So we go to the column for 0.05 with a two-tailed test and go all the way down to 16. And we can see that our critical value, our critical t value is 2.120. So we have an alpha of 0.05 and a t critical of 2.120. So we can see that our region of rejection, again, is in the blue, and there's our t critical values. So now we're going to compute and report the test statistics. So from the previous slide, we found our standard error of the mean for our sample is 2.8479, with a population mean of 100 and our sample mean of 110. So 110 minus 100 divided by the standard error of the mean of 2.8479 is 10 divided by 2.8479, which is t equals 3.51135, and it continues. So we report our t value to 2 decimals, so 3.51. So we can see that our t observed value of 3.51 falls within our region of rejection. So now we need to make a decision, and we reject the null hypothesis because t subscript 16, right, so degrees of freedom, equals 3.51, which falls within the region of rejection, and we report our conclusion. A one-sample t-test was conducted to determine how University of Memphis seniors did on the out-of-here exam compared to the national norms. The analysis produced a significant t-value, t parentheses 16 equals 3.51, p is less than 0.05. An examination of the means revealed that the University of Memphis seniors, mean of 110, standard deviation of 11.74, did significantly better than the national average, mean of 100. So our write-up, we have to write in APA style, okay? It's a very structured way to write up a results section, and it has a number of very specific parts. So there's 5 questions that you want to ask. Sorry, the bottom one got cut off a little bit. We first want to know what test was done, what was the test trying to find, or the research question, who was the sample, testing assumptions, what are the test results using actual values, our p-value, our t-value, and our degrees of freedom, and what does it mean, okay? So the first thing is a one-sample t-test was conducted. So that answers our question, what test was done? And then we need to state what was the test trying to find to determine how University of Memphis seniors did on the out-of-here exam compared to the national norm. We're not going to write any of our assumptions for one sample, but later we will. So we want to say, what are the testing results using the actual values? The analysis produced a significant t-value, t 16 equals 3.51, p is less than 0.05. And then what does it mean? An examination of the means reveals that University of Memphis seniors, mean of 110, standard deviation of 11.74, did significantly better than the national average, mean equals 100. There's some things to note, is that all of your Roman symbols, that's your M, your SD, your P, and your T, are going to be italicized. Your degrees of freedom normally goes in subscript, but y'all will not have to do that for our homework. And then we're reporting all of our values to 2 decimals, except for P, which eventually will be reported to 3 decimals. Okay, so it's 0.51, 2 decimals there, 0.74, 2 decimals there. Okay? All right, our last example here. Given that General Motors had documented that their newly designed car, named the Good Car, gets an average of 46 miles per gallon with highway driving, Mark wanted to test this statement. Mark randomly selects 10 good cars from the GM plant to use in his sample test. He assigns 10 individual drivers to the good cars for to drive 500 highway miles. Given the following data and setting an alpha at 0.05, determine whether or not GM's claims are true. Also identify the independent and dependent variable and whether it's a one-tailed or two-tailed test and the degrees of freedom. Here's our data set. So we can see that our 10 cars drove 46, 33, 43, 13, 38, 32, 28, 33, 28, and 26 miles got miles per gallon on their 500-mile highway test. Our independent variable is going to be whether they were in the sample or in the population. So all of these are going to be in the sample. Our dependent variable is miles per gallon. How many miles per gallon did they get on their 500-mile highway drive? Is it a one sample or two-tailed test? One-tailed or two-tailed test? It's going to be a two-tailed test because we don't want to know if they did better or worse than GM's claims. We just want to know if their claims are true. And the degrees of freedom is going to be 10 minus 1, so 9. So we're going to state our null hypothesis. The mean of the population of GM cars is going to be the same as the mean of what our sample represents. Over a 500 miles, the sample of good cars average is the same miles per gallon as GM indicated their cars perform. Alternative, not equal. The good test cars differ in their miles per gallon over 500 miles compared to GM cars. We're going to state the criterion for rejection, which is going to be alpha of 0.05, and we need to use our appendix B to find our T critical value. So we have a two-tailed test with alpha of 0.05. We have 10 cars in our sample, so our degrees of freedom is going to be 9. So we can see that our T critical value is 2.262. So we'll mark that on our graph, and then we're going to compute and report our test statistic. I have already found the standard error of the mean for you, so you're going to calculate your T value. It's 32 minus 46 divided by 2.9515, which is negative 14, which is negative 4.743358. So we report that to two decimals of negative 4.74. Okay, so we can see that our T value, our T observed of negative 4.74 is falling within our region of rejection. So we are going to reject the null hypothesis because T, degrees of freedom 9, equals negative 4.74, which falls within the region of rejection. And we're going to report our conclusion. Okay, so the first thing we want to do is what test did we run? A one sample T-test was conducted. We want to tell our reader what we were trying to find. To determine whether or not the sample of 10 good cars significantly differs in average miles per gallon over 500-mile test drive as compared to GM's stated average of their new models. Then we want to report our values. So the analysis produced a significant T value. T, degrees of freedom 9, equals negative 4.74, which indicates that P is less than 0.05. And then we want to tell the reader what it means. An examination of the means revealed that the sample of good cars averaged less miles per gallon, mean equals 32, than GM's stats on the new models, mean equals 46. So now we will do these exact same tests in SPSS.